Hello all, welcome to this course on time series modeling and forecasting using R. Right. So, in current week we are kind of exploring the idea of, let's say, model identification as to how do you identify the correct orders of an underlying model, right. And just to give you a brief review of where we are at now, so we started this week by looking at model identification essentially from a visual perspective. So, let's say drawing some ACF plots or PACF plots and so on and so forth. Now, again just to remind you of the problem, so let us say if you have a ARMA model which needs to be fitted on some practical data or some real data. So, how do you actually identify the optimal orders for that ARMA model? So, precisely P and Q, right. Okay. So, this is the first part. So, using visual checks, and then the second idea was using some information criteria. So, AIC, SBC, which is also called as BIC, or Hannan and Quinn criteria, or HQIC, etc. Okay. So, model identification was done there. So, once you identify the orders, then we talked about estimation, right, and then within estimation we covered broadly two ideas. So, method of moments and MLE. Okay. So, method of moments means that you, depending on how many parameters you want to estimate based on the underlying model, you create those many equations based on the population parameters and then the sample versions of that. So, let us say you equate population mean to the sample mean, you equate the population variance with the sample variance, or one can actually create or equate, let us say, population correlation with the sample correlation, right. So, depending on how many parameters you want to estimate, you create those many equations and then solve for the underlying parameters. So, this was method of moments, and then towards the end of last lecture we talked about MLE or maximum likelihood estimation. But generally speaking, in a time series framework, since our model is not really easy, be it ARMA, ARIMA, SARIMA, whatever, so we require some numerical approximation technique to solve for the parameters or to maximize that likelihood. Okay. So, how do you handle that problem is you write down the likelihood structure or rather log likelihood function, and then you try to maximize that log likelihood function. So, and then this is exactly where you require the idea of numerical approximation, because one can't maximize using a pen and paper that easily. Okay. And right towards the end we saw that how do you kind of find out the MLE based on, let us say, conditional least squares idea. So, you find out the least squares which are of course conditional, because you have to feed in the algorithm with some starting values, and then based on whatever estimators they throw you at. So, those would be the conditional least squares estimator based on maximizing the likelihood kind of. Okay. Alright, so assuming that you fix the orders or perform the model identification and the estimation, then the next step in analyzing a time series is diagnostic checking. Okay. So, what exactly you mean by this term diagnostic checking? So, let us say after identifying and estimating the model parameters, one has to assess the goodness of the fit of the model, right, which is one, and validity of all the assumptions that you are making initially. Okay. So, this idea of diagnostic checking is twofold. So, how good the fit is, and then are all the assumptions valid or not. Okay. So, firstly again just a quick revision of what assumptions we have made. So, firstly all these assumptions are based on the errors of the model, right, and then not on the actual time series, right. And what exactly are the assumptions? So, error should follow a normal distribution was one, error should be independent, all the errors should have a constant variance. So, variance should not change. Okay. So, all these were the basic assumptions, isn't it. So, if you are estimating the model and you have gotten an estimated model, so before forecasting you have to actually ensure that all the assumptions are being met or not before you move ahead with forecasting. Okay. So, this in between step is called as diagnostic checking. Okay. Or essentially this process is called as diagnostic checking. So, if the model fit is perfect, essentially you have performed all the diagnostic checks and you are kind of past that level, then one can actually go ahead and then do forecasting. Okay. Now, how can you actually perform all these diagnostic checking? So, how can you check for normality? How can you check for independence of the errors? How can you check for constant variance? So, these are some of the points that we will discuss in today's lecture and the one after this. Okay. Alright, so now the first aspect is normality of errors. So, again if you remember, one of the key assumptions that we have made earlier is that all the errors in the underlying model should follow a normal distribution of some sort. Okay. And then whatever mean, whatever variance, but then distribution should be normal. Okay. So, we actually have multiple ways of checking this hypotheses or checking this claim. So, one can actually draw a very basic histogram of the standardized residuals. Now, firstly understand that what do you mean by standardized residuals. So, standardized residual is nothing but something like ET hat. So, ET hat is the estimated residual divided by its variance. So, we are basically applying some standardization technique here, right. So, essentially standardization is what you subtract the mean and then divide by the standard deviation, right. But then if you assume that let us say mean is 0 for simplicity. So, assume mean to be 0, then you do not have to subtract anything from here, but then still divide by the underlying standard deviation. Okay. So, and then once you get hold of the standardized residuals, then you can create a histogram of the standardized residuals. Okay. Or one can actually get hold of something called as a normal QQ plot. So, QQ stands for quantile quantile. So, normal quantile plot again of the standardized residuals. Okay. Or one can look at something called as Tukey's 5 number summary. So, what does this 5 number summary stands for? It gives you several other measures along with let us say skewness and kurtosis, right. Now, all of you know probably that if the distribution has to be normal, then the skewness has to be 0 because you have a symmetric curve, right. So, since the curve is symmetric pretty much something like this, then the skewness has to be close to 0, and then kurtosis for a normal distribution should be 3. Or if you talk about excess kurtosis, so excess kurtosis means difference between the kurtosis and that of a normal distribution, which has to be basically 0, right. So, excess kurtosis should be 0 or kurtosis should be 3 basically, right. So, if all these ideas are kind of seen in the underlying data or the underlying fit, then probably we can actually see, or probably we can actually say that the underlying distribution of the errors is indeed normal. And apart from that, one can actually test out using some hypothesis testing also, which is much more formal, right. And then these are some of the tests. So, let us say Shapiro-Wilk or Jarg-Berra, etc. Okay. So, these two pairs of people, they kind of provided with some hypothesis testing to find out whether the underlying distribution is normal or not. Okay. So, this is all about normality of error. So, we will again go into a bit more detail and then try to explain some of these points here. Okay. Alright. So, for this what we will do is we will create a simulated data initially. Okay. So, if you see here, so what we are doing is we are simulating a normal white noise data. So, firstly white noise means what? So, we are assuming mean to be 0 basically. So, mean is 0. And then here we can actually fix some variance which is a constant. So, variance could be 1 or variance has to be fixed to some number. Okay. And then you look at the residuals, and then this is nothing but a histogram of the residuals. Okay. So, this is a histogram of a simulated sample from a normal distribution of size 100. So, sample size in this case is 100. So, my n is 100, right. So, what you do, so using some software you simulate a set of random observations or a set of random variables from a normal distribution, let us say having mean 0 and with some fixed variance, and then sample size is 100, and then this is the underlying histogram, right. Now, the question is that why does this histogram does not look perfectly symmetric? So, why do you think? So, if you observe this histogram here, right, so you can actually see that you have a few more observations on the left hand side of the average than on the right hand side. So, probably there might be a skew, something like that, isn't it? So, probably there might be a skew which is given by something like that, right. So, on the left hand side you have a lot of observations of the average, but then on the right hand side you do not have those many observations. So, why do you see something like this? Because the underlying distribution is normal, right. So, you have simulated from a normal distribution. So, why is it not showing you a perfectly symmetric kind of a graph? And the answer to this question is, since the sample size is relatively small. So, we are only looking at 100 observations here, right. So, now in the next slide we will see that what would happen if you kind of increase this n to let us say 1000, then what, alright. So, do we get some improved kind of histograms and so on and so forth. And by the way, there is one more thing. So, using or utilizing the same sample containing 100 observations, let us say if you simply plot the data, right. Now, again our assumption is that since it is a white noise data, the mean is assumed to be 0, right, and then here you see two colors by the way. So, red line gives you a line at 0 which is our mean, and then the blue line gives you the actual mean of the data, right? Now again the same thing. So why isn't the mean not exactly equal to 0? Because there is small difference between the red line and the blue line, right? So if you're simulating from a normal variable with mean 0, then the mean of the underlying data should also be close to 0, isn't it? But why aren't you seeing something like that? Because again the sample size is small. So n is relatively small because you only have 100 observations, okay. But what would happen again, as we discussed, if you increase this n to, let's say, something like 1000 or 5000, so would we get better approximations? The answer is hopefully yes, alright. So now we will see one more histogram and the subsequent plot, but then this time the histogram and the plot, if you compare the means, are much more better than the earlier case. And why? Because now we are creating a normal sample using not 100 but then 1000 observations, okay. So on the left hand side you have a histogram of a simulated sample from a normal distribution of size 1000, and on the right hand side you are basically plotting all those observations, x axis versus y axis, and then here you can clearly see that the red line and the blue line almost superimpose. So the mean is very close to 0, which we want, and here you can see a perfect kind of a symmetry when it comes to capturing the data, okay. So here the idea is that if the sample size is large, right, so the underlying distribution would tend to a normal distribution, okay. And then here I think many of you might have studied this idea about CLT. So CLT is central limit theorem, right. So what does the CLT tell us? So CLT tells us that the sample average kind of converges to the population average if you have a large sample. So by large sample we mean that n should be at least 30, right. And then if you have an even larger sample, then the sample average kind of converges to a population average. So my y bar would actually converge to the corresponding population mean, okay. So here we have a small comment that much closer to normality, but then again the idea is that if you want to check for normality, so probably drawing a histogram or probably confirming that what the mean is would be a good idea to start with, okay. So if the histogram is showing you some sort of a symmetric kind of a nature, then we can actually gauge that the underlying distribution might be close to a normal distribution. So this is one idea. Then the other idea is that using some formal tests like we discussed earlier. So let's say checking for normality using couple of tests. So the first one is Jarg-Bera. So by the way, Jarg-Bera are again two people, and then they propose this test of normality. And essentially, so if you see this equation here, so this JB stands for the underlying test statistic, right. So now you should understand that any hypothesis testing problem always contains or always relies on some test statistic, right. So here this capital JB that you see is the test statistic underlying the Jarg-Bera test, okay. And what goes on, or what are the ingredients in this Jarg-Bera test, are nothing but skewness and kurtosis. So skewness and kurtosis are used to construct this test statistic, which is my Jarg-Bera. So essentially what is being tested here is that you are kind of testing whether the skewness or excess kurtosis are collectively equal to 0 or not, right. So just a short while back we discussed that if the underlying distribution has to be normal, then both skewness as well as excess kurtosis should be close to 0, okay. So this Jarg-Bera kind of proposes a unique kind of a test where collectively you can actually test whether the underlying sample skewness and the sample excess kurtosis are collectively close to 0 or not, okay. And then in this period they came out with this JB test statistic and so on, and by the way this JB test statistic based on two things, so skewness and kurtosis. Okay. So let's say beta 1 and beta 2 represent skewness and kurtosis respectively. Then what exactly is the test statistic? So this JB is n by 2, and then you have a bracket, and then beta 1 hat square plus beta 2 hat minus 3 whole square divided by 4, right. And by the way, any test statistic has an underlying distribution, right. So the distribution here is a chi-square distribution with degrees of freedom 2, okay. So this JB test statistic kind of follows a chi-square distribution with degrees of freedom 2, okay. Now how do you test for something like that? So for example, if the underlying JB test statistic is bigger than the chi-square critical value, then one can actually reject the null. So by the way, this idea is a pretty standard idea when it comes to applying a hypothesis testing kind of a structure, right. So you look at the test statistic, and if the underlying value of the test statistic happens to be bigger than the tabulated chi-square value, then one can actually reject the null hypothesis. Okay. Or otherwise one can actually conclude based on the p-value also. So, if you are implementing this Jark-Bera in a software, let us say R, then R would actually give you a p-value, right. And then again the same thing. So, if the p-value happens to be less than the corresponding alpha that you have chosen, let us say 5% or 1% or 10%, whatever. So, if you are seeing something like this, then we can actually reject the null hypothesis. Okay. And by the way, rejecting the null, the conclusion is non-normality, because for a Jark-Bera test, H naught is the distribution is normal, right, or normality holds, and then the alternative hypothesis is normality does not hold. All right. So, if you are rejecting the null hypothesis, you have to go with the alternative, which kind of means that the distribution of the residuals is not normal basically. Okay. So, in this period one can actually apply some formal hypothesis tests. So, let us say Jark-Bera, or one can actually apply the second one, which is Shapiro-Wilk. So, Shapiro-Wilk is kind of similar, but then the idea is slightly different. So, a Shapiro-Wilk test statistic is a combination of ordered sample values and a particular constant generated from the means, variances and covariances of the ordered statistics of a normal distribution. So, I think this definition is slightly difficult to understand, but this capital W is the Shapiro-Wilk test statistic. And then here you see lot of ingredients, right. I mean, you see summation of AI. So, what is AI? So, AI's are some constants firstly, AI's are some constants, and then X, and then within bracket I. So, X within bracket I denotes the order statistics. So, again if somebody is not very familiar with order statistics, so what do you mean by that? So, let us say you have a sample, right. So, x1, x2 up to xn. Now, let us say you order this sample. So, order means you keep all the observations in some order, let us say increasing or decreasing, okay. And then you come up with this notation. So, x bracket 1, x bracket 2, so on, and then x bracket n. So, this is my actual sample, and then these are my order statistics for that sample. So, what do you mean by x bracket 1? So, x bracket 1 means nothing but the minimum, right, because since you ordered them, x bracket 1 is the minimum observation, x bracket 2 means the second minimum, and so on, and then x bracket n is the maximum. Okay. So, minimum, second minimum, third minimum, fourth minimum, all the way up to maximum are my order statistics for that particular sample. Okay. So, again coming back to this W, so we actually order the normal observations and then we get hold of x bracket I, and then we square those, and then in the denominator we have summation xi minus x bar square, which is kind of similar to variance, right. So, in a way what you are doing is you are basically standardizing again, isn't it. So, you are basically standardizing again. Okay. Now, again, so this test statistic is a combination like we discussed here of ordered sample values, which are xi, x bracket I, and some constants generated from the means, variances and covariances of particular order statistics of a normal distribution. Okay. And again the same thing, that one can actually reject the null if the underlying values of the test statistic are too small. Okay. So, if the values are too small, then you can actually reject the null hypothesis of normality. So, again for a Shapiro-Wilk, the hypotheses do not change. So, the null hypothesis is normality, whereas the alternative hypothesis is the distribution is not normal. So, non-normality, similar to Jark-Bera. Okay. So, in this period one can actually choose a formal testing procedure to kind of check if the underlying residuals are indeed normal or not. Okay. And one can actually have one more visual check. So, this plot is kind of called as normal QQ plot, alright. So, this plot is called as a normal QQ plot. Now, what exactly goes on in this normal QQ plot or normal quantile plot? So, firstly one should understand what you mean by quantiles. So, this term quantile. So, quantile is kind of similar to percentiles, right. So, I am sure that many of you have heard about CAT scores. So, in CAT you get percentiles, right. So, 90th percentile or 95th percentile and so on. So, by the way, what do you mean by the 95th percentile is that 95% of the candidates who have given that exam have scored less than you, right. So, if your CAT score happens to be 95th percentile or let us say 98th percentile, this means that 98% of all the candidates who appeared for CAT have scored lesser than what you have. Okay. And then quantile is kind of similar to percentile. So, the idea is clear hopefully. So, what gets plotted in this particular normal QQ plot? So, we will try to understand that. So, any normal QQ plot plots two sets of quantiles against each other. So, you have a plot like this, so x axis and y axis. So, on both the axes there should be some quantiles which are plotted. So, quantiles here and then quantiles there. So, why do you see two different quantiles is that on one of the axes we plot the theoretical quantiles of a standard normal distribution and which are plotted on the x axis. So, let us say these are the theoretical quantiles and on the y axis we plot the sample quantiles. So, sample quantiles are generated from the sample that you have or the data that you have and then theoretical quantiles are generated by assuming a standard normal distribution. So, for a standard normal distribution all the quantiles are fixed, you have like fixed numbers. For example, the 95th quantile is 1.64 and so on. So, for every possible quantile let us say 95th, 98th or 99th or let us say 88th whatever. So, for all possible quantiles you have a fixed number because the distribution is known, right, standard normal, right. So, on the y axis we plot the sample quantiles. So, sample quantiles comes from the data that you are analyzing and then on the x axis you actually plot the theoretical quantiles assuming some distribution. And essentially if this graph gives you a straight line, right, if this graph shows you a straight line then normality holds. And why is that? Because both these quantiles would match, isn't it. So, since you are plotting these two quantiles, one theoretical, the other one is sample, and if both those quantiles fall on a straight line or the graph gives you kind of a straight line, then normality holds true, right, because essentially the sample quantiles and the theoretical quantiles they match, right. So, which means that the underlying assumption which is standard normal distribution when it comes to theoretical quantiles holds true. Okay. So, this is the idea behind a normal QQ plot or a normal quantile plot. So, for example, this is a very typical kind of a normal QQ plot where normality holds, right, because almost all the points here fall on a straight line, okay, which means that the theoretical quantiles are kind of equal to the corresponding sample quantiles. And hence, which also means that the underlying distribution which kind of produces these theoretical quantiles is equal to the distribution of your data. Okay. And generally here we are taking a standard normal, right. So, we are assuming a standard normal distribution and then these are the quantiles for a standard normal distribution. So, if the theoretical quantiles and the sample quantiles they match which they are doing here, then the underlying distribution holds true. Okay. So, this is the idea about a normal QQ plot. Then probably in the next slide I will show you one plot where normality does not hold. So, let us say something like this. Okay. So, here even if you try to draw a straight line then probably the straight line would look something like that, right. But then you can see that you have lot of departures away from the straight line. So, for example, here or even here, right. So, all the points are not at all close to the straight line. So, this is a clear case where normality does not hold true basically, right. So, normality fails. So, hopefully the idea is clear. So, one can actually do lot of different checks. So, let us say create some QQ plots, create some basic histograms or let us say run some formal tests, Shapiro-Wilk, Jark-Bera, etc. and then kind of check the assumption of normality based on any practical data. Okay. Okay, so I think the first idea was checking for normality. Now, the second idea is how would you detect for serial correlation. So, in time series you have something called as serial correlation. So, what exactly you mean by serial correlation? So, generally all the residuals are found to be correlated with some of their own lagged values. So, for example, let us say ET might be correlated with let us say ET minus 4 or ET minus 1 might be correlated with ET minus 5 etc. Okay. So, let us say Et is correlated with one of its lagged value, or Et minus 1 is correlated with one of its lag value. Okay. And if you remember, the assumption is that ETs are independent. So, there should not be any correlation essentially, right. But if they are displaying some correlation, then you have some problem with the assumption. Okay. And this correlation is called as serial autocorrelation basically. Okay. So, this property is called as serial autocorrelation of the residuals. Okay. So, here the best way to kind of detect this is to draw the ACF plot. So, ACF plot is the autocorrelation function. Okay. And again on the x axis you have all the lags. So, 0, 1, 2, 3, 4 up to let us say 40. Okay. And here can you see a clear pattern when it comes to correlation. So, these correlations are all positive, these correlations are all negative, then again positive, again negative, again positive, again negative, and so on. Okay. So, if you identify all the correlations which are plotted here in this plot, then you can see a clear pattern, right. So, if you have pattern amongst the correlation, then you have a serial autocorrelation problem, because what happens is, let us say if you take any of these residuals, right, for that matter. So, let us say if you talk about ET, or rather not ET, but then let us say ET plus 10 at lag 10, something like that, and then let us say ET plus 11, or if you consider ET plus 11 and ET plus 12. Okay. So, if you look at any two consecutive correlations of errors, right, then can't you see that both the correlations are on the same side of 0? So, for example, here if you take any consecutive correlations, these are positive, or for example, here if you take any consecutive correlations, these are negative, which means that the current error and the one error in history or in the future, they are correlated, isn't it. So, same thing is happening here also. If you see any two consecutive correlations, then those are at the same side of 0. So, either positive or negative. Okay. And clearly you see some pattern also, right. So, there is some underlying pattern amongst the correlation, which means that there is some serial autocorrelation problem in the errors. Okay. So, I will give you an example where you do not have any serial autocorrelation problem. So, if you draw the ACF of the errors, now let us say these are the hypothetical bands, then as discussed earlier. So, probably after lag 1, right, all the other correlations should be inside the band or not significant. So, if something like this is happening, then we can safely say that the residuals do not possess serial autocorrelation problem, but if you have any particular pattern amongst the correlations of errors, then we can actually say that the errors have a serial autocorrelation problem. All right. And then by the way, you have some formal tests in this regard also. So, one can actually go ahead and test it formally using let us say Box and Pierce test, or let us say Lung and Box test. So, by the way, Box and Pierce developed a test to detect serial autocorrelation back in 1970, and then this was actually modified by two other people. So, Lung and Box in 1978. So, Box Pierce test or Lung and Box test are two tests for checking serial correlations are there or not. So, the underlying null hypothesis is data are independent. So, if the data is independent or if the residuals are independent, then there are no correlations, and of course, the alternative would be that you have a serial correlation problem. Okay. So, you have a serial correlation problem there. Okay. Now, what exactly is the underlying test statistic? So, again, since you are checking it formally using hypothesis test, so the underlying test statistic is given by Q Box Pierce, so BP, and the test statistic is not that difficult. So, this is based on some correlation or rather squared correlation values, if you see here. So, n into summation of rho k hat square, right, and then k goes from 1 to h. So, h is up to what lags you want to check basically, right. I mean, of course, one can't keep on checking for each and every lag, right. I mean, there should be some limit. So, h is the number of lags being tested in this Box Pierce test, and n is nothing but the sample size. And again the same criteria. So, if the value of the test statistic happens to be bigger than the tabulated chi-square value, then we can reject the null, otherwise we fail to reject the null. Okay. And then again, if you reject the null, this means that there is autocorrelation as discussed earlier on the previous slide. So, if you reject the null, you have to go with the alternative, right? So which means that there is some serial autocorrelation among the residuals. And what could be a solution here? So if serial autocorrelation persists, then the model needs to be checked again. So the model fit itself needs to be checked again, and usually it's better to add another lag in either the AR component or the MA component of the model, right. So let's say initially you propose this ARMA 1, 2 model, right, using information criteria or whatever technique, then you estimate the model, and then you are coming in the diagnostic checking kind of a framework, and then you apply this Box-Pierce test, right, and then you find out that there is indeed some serial autocorrelation problem among the errors of this model. Then what should you do? So one solution is you should probably check by adding some orders to either AR or MA component. So probably try fitting, let's say, ARMA 2.2, or probably let's say something like ARMA 1.3, for example, right, and then again do the entire exercise one more time, estimate the model, right. So once you identify the orders, then apply some information criteria to choose between these two first, right, then estimate the model, and then proceed with diagnostic checking. Okay. So in a way you can actually test out formally, much more formally, whether the distribution is normal or not, whether the errors are correlated or not, and so on and so forth. So there is one last idea, which is how do you capture changing variance problem, which we will discuss in the next lecture. Okay. Thank you.